Welcome to the fourth lecture of the linear algebra course. This lecture is about solving a system of linear equations. The video is divided into two parts. In the first part, I'll discuss basic tools and methods that are required for solving a system of linear equations. I'll talk about the general form and the matrix form of a system of linear equations. Then I'll discuss what is meant by an inconsistent system of linear equations and what is a degenerate equation. After that, I'll talk about elementary operations on a system of linear equations and the echelon form of a matrix. I'll show you how to convert a system of linear equations or a matrix into an echelon form. Echelon form is of paramount importance in solving a system of linear equations. We can determine whether a system of linear equations is consistent or inconsistent or has a unique solution or an infinite number of solutions by looking at the echelon form of the coefficient matrix. At the end of the part 1, I'll show you what a homogeneous system of linear equations is. The focus of the second part is on solving a system of linear equations. Two important methods for solving a system of linear equations are the Gaussian Elimination Method and the Gauss Jorden Method. I'll illustrate these two methods with the help of examples. I'll show you how to determine the inconsistency and the number of solutions of a system of linear equations, and finally I'll discuss how to find the basis and the dimension of the subspace spanned by a set. Let's get started. An equation is called a linear equation if the exponent of each of the unknowns does not exceed 1. This is a linear equation having one unknown x. What is the solution of this equation? By solution we mean the value of x for which the left hand side and the right hand side of the equation are equal. The solution is x equal to 8. What is the solution of these two equations? We have already seen that the solution of the first equation is x equal to 8. The solution of the second equation is x equal to 6. Let me ask another question. Is there a single value of x that satisfies both equations at the same time? In this case, the answer is no. The solution of the first equation is 8 and that of the second equation is 6. They have different solutions. What about these two equations with two unknowns x and y? Or there may be 4 equations with 3 unknowns, or 2 equations with 4 unknowns w, x, y and z. In general, there may be m equations and n unknowns. This is called a system of linear equations. The fundamental question that needs to be answered about a system of linear equations is, what is the solution that satisfies all the equations at the same time? We can write a system of linear equations in a compact form using the summation notation. A system of linear equations can also be expressed in a matrix form. The unknowns and the constants on the right hand side of the equations are arranged in column vectors and the coefficients are arranged in a matrix form. The multiplication of the ith row of the coefficient matrix with the column vector of the unknowns is equal to the ith equation. We can write the whole system of linear equations as Ax equal to b. The matrix A is called the coefficient matrix. Let's look at some examples of linear equations and the associated matrix forms. This system of linear equations has 3 equations and 3 unknowns, and this is the associated matrix form. 3 equations, 2 unknowns and the associated matrix form. The system of linear equations with 2 equations and 4 unknowns has this matrix form. Not all systems of linear equations have a solution. Such systems are called inconsistent. I show you an example of an inconsistent system of linear equations. We have a system of 3 linear equations with 2 unknowns x and y. Let us consider a possible solution with x equal to 2 and y equal to -1. I have expressed it in a column vector form. Let us see if it satisfies all the 3 equations. Substitute x equal to 2 and y equal to -1 in the first equation. You can see that this candidate solution satisfies the first equation. Let us substitute these values in the second equation. The second equation is also satisfied by these values of x and y. Now let us try the third equation. The result of the substitution is 5, but the result should be equal to 1 because the right hand side of the equation is 1. So these values of x and y do not satisfy the third equation. Therefore x equal to 2 and y equal to -1 cannot be the solution of this system of linear equations. Let us consider another possible solution with x equal to 0 and y equal to 1. Let us substitute it in the first equation. The result of the substitution matches with the right hand side of the first equation, so this candidate solution satisfies the first equation. Second equation. The right hand side of the second equation, which is equal to 3, does not match the result of the substitution, which evaluates to -1. It does not satisfy the second equation. However, it does satisfy the third equation. X equal to 0 and y equal to 1 is not the solution as it does not satisfy the second equation. The third possible solution with x equal to 1 and y equal to -2 satisfies the last two equations but does not satisfy the first equation. You see that there is no single solution that satisfies all the three equations at the same time. Such a system of linear equations is called an inconsistent system of linear equations. You may think that the linear equations are inconsistent if there are more equations than the number of unknowns. That is not generally true. The system of linear equations may be consistent even if the number of equations is greater than the number of unknowns. Later in this video, I'll show you how we can determine if a system of linear equations is inconsistent. An equation with all the coefficients equal to 0 and with a non-zero right hand side is called a degenerate equation. A degenerate equation is always inconsistent no matter which values of unknowns we use. A system of linear equations is inconsistent if it contains a degenerate equation. Does a system of linear equations contain a degenerate equation in practice? Indeed, a system of linear equations may contain a degenerate equation in a hidden form. We will see this later in this video. There are some operations on a system of linear equations, or you can say that some special modifications of equations that do not affect the solution. One of them is multiplying an equation with a constant. Let me illustrate it with the help of an example. Here are two simultaneous equations with two unknowns. You see that x equal to 5 and y equal to -2 is the solution because it satisfies both equations. Now let us multiply the first equation by 13 and the second equation by 8. The resulting system of linear equations is 13x plus 13y equal to 39 and 8x minus 8y equal to 56. Let us try the same solution in this modified system of linear equations. The same solution satisfies the modified form of linear equations as well. The solution is not affected. Let us look at another operation that also preserves the solution. We have two simultaneous equations 2x plus 3y equal to 7 and 5x minus 4y equal to 6. The solution of these equations is x equal to 2 and y equal to 1. Let's create another system of linear equations by modifying the original system. Take the first equation as it is and modify the second equation by adding to it 0.3 times the first equation. We multiplied the first equation by 0.3 and added it to the second equation. Now replace the second equation with the new equation. In this way, we have created a new system of linear equations in which the first equation is the same and the second equation is modified. Let us verify the same solution to see if it satisfies the new system of linear equations. Substitute x equal to 2 and y equal to 1 in the new system of linear equations. The same solution satisfies the new equations as well. The solution remains the same even if we have modified the second equation. Such operations which do not affect the solution are of great importance in solving a system of linear equations. We can modify the system however we want and convert it to our desired form for which the solution can easily be found. The operations that do not affect the solution are called elementary operations. There is one more elementary operation, that is interchanging any two equations. The solution will remain the same even if we interchange any two equations. We have already seen the elementary operation of replacing an equation with its scalar multiple. And the third elementary operation is replacing an equation with the sum of this equation and the multiple of another equation. Symbolically, we write the interchange of two equations as interchange EI and EJ, or EI double arrow sign EJ. We express the second elementary operation as replace EI by A times EI, or A times EI arrow sign EI. The third elementary operation has the symbolic representation like this. In the arrow notation, the left hand side is the new equation and the right hand side is the equation that is replaced. We can also perform the same operations on a matrix. We can interchange any two rows, multiply a row with a scalar, or add multiple of one row to another row. We will see the significance of elementary operations in the second part of this video when we will solve the system of linear equations. Earlier I mentioned that we can transform a system of linear equations into a convenient form using elementary operations to find the solution. The special name for that convenient form is the echelon form. The echelon form of a system of linear equations provides us with all the required information, whether the equations are consistent or inconsistent, have a unique solution or an infinite number of solutions, and so on. Let us see what an echelon form of a system of linear equations looks like. Look at this system of three linear equations with three unknowns x, y, and z. The first variable with a non-zero coefficient in each equation is called the pivot variable. X is the pivot variable in the first equation, y is the pivot variable in the second equation, and z is the pivot variable in the third equation. Here is another system of two linear equations having four unknowns. W is the pivot variable in the first equation and y is the pivot variable in the second equation. Now look at these three systems of linear equations, and these are the pivot variables. If you compare these four systems of linear equations, you see that each equation has a different pivot variable in each row in the first two systems of linear equations. However, these two systems do not have a distinct pivot variable in each equation. The system of linear equations having distinct pivot variables is called the echelon form. There is one more condition for a system of linear equations to be an echelon form. Although this system of linear equations has a distinct pivot variable in each equation, this is not an echelon form. The other condition is that the pivot variable in the following equation should be strictly to the right of the pivot variable of the preceding equation. In this system of linear equations, x is the pivot variable of the second equation and is to the left of the pivot variable of the first equation. Therefore, this is not an echelon form. So, a system of linear equations is in echelon form if all the equations have a distinct pivot variables, and secondly, pivot variable of the following equation must be strictly to the right of the pivot variable of the preceding equation. Analogous to the system of linear equations, a matrix also has an echelon form. The first non-zero element of each row is called a pivot. The first property of the echelon form of a matrix is that each column does not have more than one pivot element, and the second property is that the pivot element of the following row should be strictly to the right of the pivot element of the preceding row. This is an echelon form of a matrix. The pivot element of the first row is 2, of the second row is -3, and of the third row is 7. A reduced echelon form is similar to an echelon form with a minor difference. An echelon form is called a reduced echelon form if each of the pivot elements is equal to 1, and if a column contains a pivot element, then all other elements of that column are 0. This is the reduced echelon form of a matrix. First, note that the matrix is in echelon form. Second, each of the pivot element is 1. And third, the columns containing the pivot element have all zeros except the pivot element. A system of linear equations also has a reduced echelon form. An echelon form is called a reduced echelon form if the coefficient of each pivot variable is 1, and if a variable is a pivot variable in one equation, then its coefficient is 0 in all other equations. This system of linear equations is in the reduced echelon form. This is another reduced echelon form of a system of linear equations. W and Y are pivot elements and their coefficients are 1. The coefficient of Y is 0 in the first equation and the coefficient of W is 0 in the second equation. So this is a reduced echelon form. It is more convenient to manipulate the matrix form of a system of linear equations to find the solution. Here is a system of 3 linear equations with 3 unknowns, and this is the coefficient matrix. We also need to combine the constants on the right hand side of the equations with the coefficient matrix to perform elementary operations in matrix form. This matrix is called the augmented coefficient matrix or simply the augmented matrix. Let us perform an elementary operation on the equations as well as on the augmented matrix. You will see that both ways are equivalent. Let us multiply the first equation by 1/2. The new system looks like this. Only the first equation is altered. Now perform the same elementary operation on the associated augmented matrix, and here is the resulting matrix. If you look closely, the new augmented matrix is again the augmented matrix of the new system of linear equations. I have illustrated this with just one elementary operation. If we perform other elementary operations on the equations and the associated augmented matrix, the new augmented matrix will represent the new system of linear equations. So we can equivalently perform the elementary operations on the augmented matrix because the linear equations in the matrix form are easier to work with. One last concept before moving to the second part of the video: a homogeneous system of linear equations. A system of linear equations having all zeros on the right hand side is called a homogeneous system of linear equations. It has the matrix form Ax equal to 0 vector. An important property of a homogeneous system of linear equations is that its solution is a subspace of Rn, where n is the number of unknowns and the vector space Rn is the set of all ordered n tuples. Let's prove it. A column vector of all zeros is always the solution of a homogeneous system of linear equations. Therefore, the solution set S contains the null vector. Now suppose x1 and x2 are two solutions of the homogeneous system of linear equations and k is a real number. Ax1 and Ax2 are equal to the null vector because we assume that they are solutions of the homogeneous equations. Multiply the coefficient matrix A with kx1 plus x2 and the result is again the null vector. Therefore, kx1 plus x2 is also a solution. Let me summarize it. A subset must have two properties to be a subspace. First, the subset must contain the null vector, and second, if x1 and x2 are two elements in the subset and k is a scalar, then kx1 plus x2 also belongs to the same subset. I have shown that the solution set S of a homogeneous system of linear equations contains the null vector, and secondly, if x1 and x2 are in the solution set S and k is a scalar, then kx1 plus x2 also belongs to the solution set. Therefore, the solution of a homogeneous system of linear equations is a subspace of Rn. So far, I have shared with you the basic concepts, methods, and tools that are required for solving a system of linear equations. Let's move on to the main part of the video where I'll illustrate two important methods for finding solution of a system of linear equations. In this part of the video, we will study two important methods for solving a system of linear equations, the Gaussian Elimination Method and the Gauss Jorden Method. Then we will see how we can determine whether a system of linear equations is consistent or inconsistent, and if it is consistent, how many solutions it has, a unique solution or an infinite number of solutions. We will see what is meant by the rank of a matrix. In the previous videos, we saw that the span of a set was a subspace. I postponed finding the basis and dimension of the span of a set because it depended on the methods that we studied in this video. We will also see how to determine the basis and dimension of the span of a set. Gaussian elimination and the Gauss Jorden are the two important methods for solving a system of linear equations. There are two main steps in both methods. First, convert the system of linear equations or the associated augmented matrix to the echelon form. If there is a degenerate equation in the echelon form, then the equations are inconsistent and therefore have no solution. And if the equations are consistent, we go to the second step. In the second step, use back substitution to find the complete solution. I'll illustrate both steps with the help of examples. The difference between the Gaussian elimination method and the Gauss Jorden method is that we convert the equations or the matrix into an echelon form for applying the Gaussian elimination method, whereas we convert it into the reduced echelon form for the Gauss Jorden method. Our first example has two equations and two unknowns. First, we write the augmented matrix B. Now we will perform a series of elementary operations to convert the augmented matrix to the reduced echelon form. In the first step, we make the first element of the first row equal to 1. So we multiply the first row by 1/2. Now we make each of the elements equal to 0 below the pivot element of the first row. So we replace the second row with R2 minus 5R1. In the third step, we multiply the second row by minus 2 over 23 to make the pivot element equal to 1. And in the last step, we make the element above the pivot element of the second row equal to 0 by replacing the first row with R1 minus 3 by 2 R2. We have converted the augmented matrix to the reduced echelon form, and the solution can easily be read from the reduced echelon form. These equations have a unique solution x equal to 3 and y equal to 4. The second example again has two equations and two unknowns. Write the augmented matrix. Replace R2 by R2 minus 3R1. Now observe the second row of the augmented matrix. This is a degenerate equation 0x plus 0y equal to 1. Therefore, the equations are inconsistent and have no solution. Let us solve another system of two linear equations with two unknowns. Write the augmented matrix B. Make the first element equal to 1 by multiplying the first row by 1 over 5. Now replace the second row with R2 minus 15 R1. Although the second equation has vanished, but it is not degenerate. X is the pivot variable of the first equation. The non-pivot variables are called free variables. They can have arbitrary values. Free variables are the variables that are not pivot in any of the equations. So, if a system of linear equations has one or more free variables in the echelon form and does not contain a degenerate equation, then it has an infinite number of solutions because the free variables can have arbitrary values. This system of two linear equations has an infinite number of solutions because y is not a pivot variable in any of the equations and therefore it is a free variable. Let us move on and find out what the solutions look like. First, let's convert the echelon form to the equation form. Now express the pivot variables in terms of free variables. X is equal to 3y plus 2 divided by 5. And here is the complete solution. We have replaced the free variable y with the parameter t. X equal to 3t plus 2 divided by 5 and y equal to t is the solution for any value of the parameter t. Our next example has 5 equations with 3 unknowns. Let us solve these equations. Write the augmented matrix B. Multiply the first row by 1 over 3 to make the first element equal to 1. Now we perform 4 elementary operations in the same step to make the first elements of all the rows equal to 0 except the first element of the first row. We replaced R2 with R2 minus 5R1, R3 with R3 minus 2R1, R4 with R4 minus 8R1 and replaced R5 with R5 plus 4R1. In the next step, we multiply the second row by minus 1 over 19.33 to make the pivot element of the second row equal to 1. We need to make each element equal to 0 above and below the pivot element of the second row. Let us perform 4 elementary operations in the same step. Replace R1 with R1 minus 1.67 R2. Replace R3 with R3 plus 6.33 R2. Replace R4 with R4 plus 1.33 R2 and replace R5 with R5 minus 16.67 R2. Let us move on to the third row and multiply it by minus 1 over 2.919 to make the pivot element equal to 1. Again, perform 4 elementary operations to zero out all the elements above and below the pivot element of the third row. We have converted the augmented matrix to the reduced echelon form. The augmented matrix does not have a degenerate equation, and secondly, all the unknowns are pivot elements. There are no free variables, therefore these equations have a unique solution: x equal to 5, y equal to minus 7 and z equal to 12. In this example, we have 5 equations with 3 unknowns. First, write the augmented matrix and convert it into an echelon form or the reduced echelon form using elementary operations. I have converted it into an echelon form. The echelon form does not contain a degenerate equation, so the equations are consistent. Now convert the echelon form into equation form. The unknowns x and y are pivot variables, whereas the unknown z is a free variable. The equations have an infinite number of solutions. We will express the pivot variables in terms of the free variable. X is equal to 8.5581 minus 0.186 divided by 4, and y is equal to 26.75 plus 9z divided by 10.75. The value of the variable z can be arbitrarily chosen. The complete solution of the equations has the form. We change the free variable to the parameter t. You can verify that this solution will satisfy all the 5 equations for any value of t. The solution lies on a straight line in a Cartesian coordinate system. This example also has 5 equations with 3 unknowns. Write the augmented matrix and perform 4 elementary operations to make all the elements equal to 0 below the first pivot element. All the equations except the first equation have vanished. It means that there is effectively only one equation. There is no degenerate equation, so the equations are consistent. X is the pivot variable and y and z are the free variables. We will express x in terms of the free variables y and z. X is equal to 3y minus 4z minus 4 divided by 5. And here is the complete solution. We have replaced y and z with the parameters t1 and t2. Although there are infinite number of solutions for both systems in the current example and in the previous example, the previous solution has one parameter, whereas this solution has two parameters. This solution represents a plane in a three-dimensional Cartesian coordinate system, whereas the solution of the previous example represented a straight line in a three-dimensional coordinate system. This is the last example of a non-homogeneous system of linear equation. Let us summarize what we have learned. First, we convert the augmented matrix into an echelon form or the reduced echelon form. The echelon form is not unique. You may come up with different echelon forms of the augmented matrix, but the final solution will be the same. In the second step, observe the echelon form to see if it has a degenerate equation, and if it has, then the equations are inconsistent. However, if the equations are consistent, we express the pivot variables in terms of the free variables. If there are no free variables, then the equations have a unique solution. If there is one free variable, the solution has one parameter and it represents a straight line. A solution with two parameters represents a plane. Now we will look at 3 examples of a homogeneous system of linear equations. Homogeneous linear equations are always consistent because they have at least one solution, that is the zero vector or the null vector. However, homogeneous linear equations can have an infinite number of solutions. Let us solve this system of 4 homogeneous linear equations. We need not write the augmented matrix, we only need the coefficient matrix because the right hand side of the equations always remains 0 after every elementary operation. Here is the coefficient matrix and we have converted it into the reduced echelon form. You see that there are no free variables. All the 3 unknowns x, y and z are pivot variables. So these equations have a unique solution, which is the zero vector. Earlier we saw that the solution of a homogeneous system of linear equations was a subspace of Rn, in this case a subspace of R3. The basis of the solution subspace S is the empty set and the dimension of S is 0. This is second example of a homogeneous system of linear equations. We have 4 homogeneous linear equations with 3 unknowns. First we write the coefficient matrix and we convert the coefficient matrix to the reduced echelon form. I have already explained how we can convert a matrix to an echelon form, therefore I have skipped the steps of performing elementary operations. Obtain the equations form from the echelon form. X and y are the pivot variables and z is the free variable, so we express x and y in terms of z. We parameterize the solution by replacing z with the parameter t. The equations have an infinite number of solutions. We can obtain the basis of the solution subspace by substituting any real number for t. Let us substitute 1 for t. Therefore, the basis of the solution set S is -4, 7, 1. As the basis contains one vector, the dimension of the solution subspace is 1. The last example of a homogeneous system of linear equations. Here is the coefficient matrix. We convert it to the reduced echelon form and obtain the equations form from the echelon form. X is the pivot variable and y and z are the free variables. Express x in terms of y and z. Now replace y with the parameter t1 and z with the parameter t2, and here is the parametric form of the solution. The solution set contains an infinite number of solutions. The dimension of the solution set S is equal to the number of free variables or the number of parameters. The solution has two parameters t1 and t2, therefore its dimension is equal to 2. We can find the basis vector corresponding to the parameter t1 by substituting 1 for t1 and 0 for t2. And we can obtain the second basis vector by substituting t1 equal to 0 and t2 equal to 1. Here are the two basis vectors. The first basis vector corresponds to t1 equal to 1 and t2 equal to 0, and the second basis vector corresponds to t1 equal to 0 and t2 equal to 1. The dimension of S is equal to 2. The rank of a matrix is an important concept in linear algebra. Let us see the definition of the rank of a matrix. Suppose A1, A2 and A3 are three coefficient matrices of three different homogeneous systems of linear equations. These are the respective reduced echelon forms of A1, A2 and A3. The matrix A1 has three non-zero rows in its echelon form, and all the three unknowns are pivot variables. Therefore, it has a unique solution and the dimension of the solution is 0. The matrix A2 has one free variable and the dimension of the solution is equal to 1. The matrix A3 has two free variables, so the dimension of the solution for the third system of equations is equal to 2. It is evident that the number of non-zero rows in the echelon form determines the dimension of the solution. The number of non-zero rows in the echelon form of a matrix determines very important characteristics of the matrix and the associated system of linear equations. In literature, the number of non-zero rows in the echelon form is called the rank of the matrix. Here is the formal definition. If M is any matrix and we convert it to echelon form, then the number of non-zero rows in the echelon form is called the rank of the matrix M. The respective ranks of the matrices A1, A2 and A3 are 3, 2 and 1. Let us see how we can determine the dimension of the solution. The dimension of the solution of a homogeneous system of linear equations is equal to the number of variables n minus the rank of the coefficient matrix. The dimension of the solution set S1 is 3 minus the rank of A1. The dimension of the solution set S2 is 3 minus the rank of A2, and the dimension of S3 is 3 minus the rank of A3. Let us see how the rank of the coefficient and the augmented matrices can determine whether a non-homogeneous system of linear equations is consistent or inconsistent. Suppose B is the augmented matrix of a system of linear equations. This is the echelon form of the augmented matrix B. You see that there is one degenerate equation, so the equations are inconsistent. Notice that the rank of the matrix B is equal to 2. A is the coefficient matrix of the same system of linear equations and has the echelon form. Now compare the echelon forms of both matrices. The rank of A is equal to 1 and the rank of B is equal to 2. Here is the rule to check if a system of linear equations is inconsistent. If the rank of the augmented matrix B is greater than the rank of the coefficient matrix A, then the associated system of linear equations is inconsistent. If both ranks are equal, then the equations are consistent. In most cases, converting both matrices to echelon form is not required. We can simply observe the echelon form of only the augmented matrix to see if it contains a degenerate equation. We can also determine the number of solutions of a non-homogeneous system of linear equations using the rank of the augmented matrix B. A consistent system of linear equations can have either a unique solution or an infinite number of solutions. Let us see how the rank can determine this. Step 1. Convert the coefficient and the augmented matrices to the echelon form. If the rank of B is greater than the rank of A, then the equations are inconsistent and have no solution. We can reduce our effort by simply observing the echelon form of the augmented matrix only. If it contains a degenerate equation, then the equations are inconsistent. We will not require conversion of the matrix A to the echelon form. The equations are consistent if the rank of B is equal to the rank of A. So, if the rank of B is equal to the rank of A, we need to decide whether there is a unique solution or an infinite number of solutions. Compare the rank of B with the number of unknowns. If the number of unknowns is greater than the rank of B, then there is an infinite number of solutions. Otherwise, if the number of unknowns is equal to the rank of B, then the equations have a unique solution. A homogeneous system of linear equations is always consistent. So, for a homogeneous system of linear equations, we only need to determine the unique solution or the infinite number of solutions. First, convert the coefficient matrix A to echelon form. Then compare the rank of A with the number of unknowns. If the number of unknowns is greater than the rank of A, the equations have an infinite number of solutions. Otherwise, if the number of unknowns is equal to the rank of A, the equations have a unique solution, the null vector. In the previous video, we have seen the definition of a linearly independent set. Let us now see how we can find if a set S is linearly independent. Suppose a subset S of Rm contains n vectors, and suppose the first vector is denoted by v1, the second vector by v2, and the nth vector by vn. Recall the definition of linearly independent vectors. v1, v2, and vn are linearly independent if the equation has a unique solution in which all the unknowns are equal to 0. Substitute the actual vectors and expand it. This looks like solving a homogeneous system of m linear equations with n unknowns. If these equations have a unique solution, the set S is linearly independent. Otherwise, it is linearly dependent. Here is the coefficient matrix. We can determine the number of solutions using the method based on the rank of the coefficient matrix. If the rank of A is greater than the number of unknowns, then the equations have an infinite number of solutions. The number of unknowns is equal to the number of vectors. So, if the rank of A is equal to the number of vectors, the set S is linearly independent. Otherwise, if the rank of A is less than the number of vectors, the set S is linearly dependent. Let us summarize the method to determine linear independence. Step 1. Create a matrix A whose columns are the vectors. Step 2. Find the rank of the matrix A. If the rank of A is equal to the number of vectors, the set S is linearly independent. And if the rank of A is less than the number of vectors, the set S is linearly dependent. The last topic of this video is about finding the basis of the span of a subset S of Rn. Suppose a subspace of Rn is spanned by a set S. S may not be the basis. Let us see how we can find the basis of the subspace spanned by S. Step 1. Arrange the vectors as rows of a matrix A. Step 2. Convert the matrix A into echelon form or reduced echelon form. The dimension of the subspace spanned by S is equal to the rank of the matrix A, and the non-zero rows are the linearly independent vectors that span the subspace S. Therefore, the basis vectors of the span of S are the non-zero rows in the echelon form of the matrix A. This is another important property of the echelon form. The non-zero rows are linearly independent, and row vectors that vanish in the echelon form are those vectors that can be written as a linear combination of the other vectors. Therefore, they vanish in the echelon form. We stop this video lecture here. See you in the next video. In the coming video, I'll talk about linear transformations. I need your support to grow this channel, and your subscription to this channel will help me greatly. If you haven't already subscribed, please subscribe. See you in the next video. Bye bye.